You're holding your phone right now, feeling its weight, its smooth surface against your fingertips. Every atom in that device, every carbon molecule in your skin, every oxygen particle flowing through your lungs at this very moment, none of it should exist. According to the fundamental laws of physics, we should be living in a universe of pure energy, where matter never formed, where complexity never emerged, where you and I would never have come into being. And yet, here we are. The question that has haunted physicists for decades is deceptively simple. How did we get something from what appears to be nothing? How did the raw energy of the early universe transform into the intricate atomic structures that make up literally everything around you? Tonight, we're going to unravel one of the most profound mysteries in all of science. The story of how atoms, those invisible building blocks of reality, emerged from the cosmic void. Now, I know what you might be thinking. This sounds like heavy science, complex equations, the kind of stuff that puts you to sleep in textbooks. But here's the thing, this isn't just abstract physics, this is your origin story. Every single atom in your body was forged in conditions so extreme, so violent, so unlikely that the very fact you're conscious and wondering about this right now borders on miraculous. What we're about to explore will challenge everything you think you know about how reality works. We'll dive into moments when the universe was smaller than the period at the end of this sentence, yet contained all the energy that would eventually become every star, every planet, every living thing that has ever existed. We'll witness the cosmic dance of forces so fundamental that they literally shaped the architecture of existence itself. If you find comfort in these gentle explorations at the intersection of science and mystery, I'd be grateful if you'd consider subscribing or hyping up this video with hype points. The visuals are here for you, but feel free to close your eyes, breathe deep, and let your imagination drift through these quantum possibilities. Also, I'd love to know where you're contemplating from tonight. Comment your time and location below. Let's begin. Before we journey back to those first incredible moments, let me tell you why this story matters more than you might realize. See, understanding how atoms formed isn't just about satisfying scientific curiosity. It's about grasping the most important truth of your existence. You are not separate from the universe. You are the universe. The calcium in your bones, the iron in your blood, the carbon that forms the backbone of your DNA, all of it emerged from processes so extraordinary that they make the most imaginative science fiction seem mundane by comparison. The journey we're about to take spans nearly 14 billion years, from the first trillionth of a second after the Big Bang, to the moment complex atoms became stable enough to eventually form molecules, then cells, then consciousness, capable of pondering its own existence. And here's what's truly mind-blowing. This entire cosmic symphony of creation happened according to rules so precise, so perfectly calibrated that if any of the fundamental constants of physics were different, by even the tiniest fraction, atoms would never have formed at all. Let me give you a preview of just how incredible this story becomes. In the beginning, there were no atoms. There weren't even the building blocks that would become atoms. The universe was a thing of pure energy, so hot that particles couldn't hold together for more than an instant before being torn apart by the cosmic violence surrounding them. Yet, within the first few minutes of existence, through a series of events that required perfect timing and impossible precision, the first simple atomic nuclei began to emerge from this chaos. We're talking about hydrogen and helium, the simplest possible atoms. But even these required conditions so specific that they could only exist within a narrow window of cosmic time too early. And the universe was too hot for anything to stick together, too late, and the expanding cosmos would cool beyond the point where nuclear fusion could occur. The window for creating the first atoms lasted mere minutes in a universe that would go on to exist for billions of years. And that's just the beginning, because those first simple atoms would eventually give birth to stars. And inside those stellar furnaces, under pressures and temperatures that dwarf anything we can create on Earth, heavier elements would be forged. Carbon, oxygen, nitrogen, iron. The periodic table we memorized in school represents a cosmic cookbook with each element requiring its own specific recipe of temperature, pressure, and time to come into existence. But here's where the story gets really wild. The atoms that would eventually form you didn't just appear once and stay put. They've been recycling through the universe for billions of years. The carbon in your cells was created in the core of a dying star that exploded long before our solar system existed. The oxygen you're breathing right now has been part of countless other molecules, other organisms, other worlds. You are literally made of recycled stardust that has been on an incredible journey through space and time. Tonight we're going to trace that journey from the very beginning. We'll start in the first moments after the Big Bang, when the universe was nothing but an expanding fireball of energy. We'll watch as that energy began to cool and condense, allowing the first particles to form. We'll witness the cosmic battle between matter and antimatter, a war that nearly resulted in a universe with no atoms at all. We'll explore the mysterious process of nucleosynthesis, when the first atomic nuclei were welded together in the cosmic furnace of the early universe. Then we'll fast forward through the Dark Ages, that long period when atoms existed, but stars had not yet formed to light up the cosmos. We'll see how gravity worked patiently to pull atoms together into the first stellar nurseries, where new elements would be cooked up in nuclear reactors millions of times more powerful than anything humans have ever built. But this isn't just a story about physics and chemistry. It's a story about emergence, about how simple things can combine to create complexity beyond imagination. Each step in atomic formation opened up new possibilities that didn't exist before. When hydrogen and helium first formed, they made possible the birth of stars. When stars began fusing heavier elements, they made possible the formation of planets. When planets formed with the right chemical ingredients, they made possible the emergence of life itself. And here's the part that should give you chills. This entire process, from the formation of the first atomic nuclei to the complex molecules that make up your brain, happened without any conscious guidance or design. The universe discovered how to create atoms through pure trial and error, through the relentless application of simple physical laws over vast spans of time. What we're looking at is creativity on a cosmic scale. The universe literally inventing new forms of complexity through the patient accumulation of simple interactions. The more we understand about atomic formation, the more we realize how precarious our existence truly is. There are so many ways this story could have gone wrong. If the strong nuclear force was slightly weaker, atomic nuclei would fall apart. If it was slightly stronger, hydrogen would be consumed so rapidly that stars couldn't form. If the electromagnetic force had a different strength, electrons couldn't orbit nuclei in stable patterns. The universe seems to exist in a narrow band of possibility, where atoms can form, where complexity can emerge, where consciousness can eventually ask questions about its own origins. Let me give you a preview of just how incredible this story becomes. In the beginning, there were no atoms. There weren't even the building blocks that would become atoms. The universe was a thing of pure energy, so hot that particles couldn't maintain their individual identities. Picture a cosmic soup where energy and matter were completely interchangeable, where particles popped into existence only to be instantly destroyed by collisions with other particles moving at nearly the speed of light. As the expansion continued and temperatures began to drop, something remarkable started to happen. The quarks began to find each other and stick together, forming the first protons and neutrons. This process, called confinement, was like the universe suddenly discovering how to make the first stable building blocks. But even these protons and neutrons weren't safe yet. The environment was still far too hostile for anything resembling an atom to form. Think of it like trying to build a house during a hurricane while someone keeps throwing dynamite at your construction site. Every time particles tried to bond together, the intense heat and constant collisions would tear them apart almost instantly. This brings us to one of the most crucial windows in cosmic history. Scientists call it Big Bang Nucleosynthesis, and it lasted for only about 20 minutes. 20 minutes out of nearly 14 billion years of cosmic evolution. And yet during this brief window, the universe accomplished something extraordinary. It created the first atomic nuclei. The process began when protons and neutrons, those building blocks that had formed earlier, started sticking together through the strong nuclear force. But this wasn't random. The universe had to maintain exactly the right conditions for nuclear fusion to occur. Too hot, and the newly formed nuclei would be blasted apart by high-energy photons. Too cool, and the particles wouldn't have enough energy to overcome their electrical repulsion and fuse together. During these 20 minutes, the cosmic nuclear reactor was working at full capacity. Protons fused with neutrons to create deuterium, a heavy form of hydrogen. Deuterium nuclei then combined with additional protons and neutrons to form helium-3 and helium-4. Some small amounts of lithium were also produced. But here's the crucial point. The universe couldn't make anything heavier than lithium during this period. The conditions weren't right for forming carbon, oxygen, iron, or any of the other elements that would eventually become essential for planets and life. So, at the end of this cosmic cooking session, the universe had successfully created its first atomic nuclei, but they were still naked nuclei, stripped of electrons and unable to form complete atoms. The environment was still far too hot and energetic for electrons to settle into stable orbits around these nuclei. What the universe had accomplished was creating the raw materials for atoms, but not atoms themselves. This brings us to one of the most important concepts in understanding how atoms formed from nothing. The universe had to learn patience. After that initial burst of nucleosynthesis, cosmic evolution entered a much slower phase. The newly formed nuclei had to wait, suspended in a sea of high-energy radiation and free electrons for conditions to become just right for complete atom formation. Think about the incredible precision required for this process to work. The universe had to expand at exactly the right rate to allow temperatures to cool gradually. If expansion happened too quickly, the density would drop too fast, and nuclear fusion couldn't occur. If expansion happened too slowly, the universe would collapse back on itself before atoms could form. The cosmic expansion rate had to be calibrated with extraordinary precision for matter to have any chance of existing. But there's another layer to this story that makes it even more remarkable. During this entire process, the universe was also solving the problem of why anything exists at all. You see, according to our understanding of physics, the Big Bang should have created equal amounts of matter and antimatter. And when matter meets antimatter, they annihilate each other completely, converting back into pure energy. If the universe had created exactly equal amounts of matter and antimatter, everything would have been destroyed, leaving behind nothing but photons of light racing through empty space. No atoms, no stars, no planets, no life. The fact that we exist at all means that somehow, for reasons we still don't fully understand, there was a tiny imbalance in favor of matter over antimatter. We're talking about an incredibly small difference. For every billion antimatter particles, there were about 1,000,000,001 matter particles. That single extra particle of matter multiplied across the entire universe became everything we see today. Every atom in your body, every star in the sky, every galaxy stretching across billions of light years, all of it comes from that minuscule cosmic asymmetry. This realization should fundamentally change how you think about your own existence. You're not just unlikely, you're the product of the most improbable series of events in cosmic history. The atoms that make up your body survived a cosmic annihilation event that destroyed nearly everything that existed in the early universe. You are literally made from the survivors of the greatest catastrophe in the history of reality. As we continue deeper into this story, we'll discover how those surviving atomic nuclei eventually captured electrons to become complete atoms, how those atoms learned to bond with each other to form molecules, and how molecules eventually organize themselves into structures complex enough to contemplate their own origins. But first, we need to understand the cosmic dark age that followed nucleosynthesis. A period when atoms existed, but the universe had not yet learned how to make them shine. The stage was set for the next chapter in atomic evolution, but the universe still had several major obstacles to overcome before the matter we're made of could truly flourish. The universe was about to enter what cosmologists call the Dark Ages, and the name is brutally accurate. For hundreds of thousands of years, the cosmos would remain shrouded in an impenetrable fog, a cosmic blindness that prevented light from traveling freely through space. But this darkness wasn't empty, it was pregnant with potential, filled with atomic nuclei, desperately waiting for their chance to become complete atoms. Picture the universe at this stage as a vast ocean of glowing plasma where atomic nuclei and electrons existed separately, unable to come together, because the ambient temperature was still too high. Every time an electron tried to settle into orbit around a nucleus, high-energy photons would smack into it and knock it loose again. It was like trying to build a delicate house of cards during an earthquake, where every attempt at construction was immediately demolished by the chaotic environment. This cosmic fog was opaque because photons, the particles of light, couldn't travel very far without bumping into a free electron. Imagine trying to see through a thick blanket of steam, except this steam filled the entire observable universe. Light would travel maybe a few thousand miles before getting scattered in a random direction, making the cosmos effectively invisible to itself. But the universe was expanding, and with that expansion came cooling. Temperature was dropping steadily, and the cosmic plasma was gradually losing its violent energy. The universe was approaching a critical threshold, a moment when electrons would finally have enough stability to be captured by atomic nuclei and remain in stable orbits. When that moment arrived, it would be one of the most dramatic transitions in cosmic history. Scientists call it recombination. though that's actually a misleading name because electrons and nuclei weren't recombining, they were combining for the very first time in the universe's existence. This was the birth of the first complete atoms. The process began when the cosmic temperature dropped to about 3,000 degrees Kelvin. Now that might still sound incredibly hot, and it is by Earth standards, but remember we're comparing this to conditions that were once trillions of degrees. At 3,000 degrees, something magical became possible. Electrons could finally settle into the lowest energy orbit around hydrogen nuclei without being immediately kicked out by ambient radiation. When this happened, the change was swift and dramatic. Within a relatively short cosmic time span, roughly 100,000 years, most of the free electrons in the universe were captured by atomic nuclei. Hydrogen atoms formed in vast quantities along with helium atoms and trace amounts of lithium atoms. For the first time in cosmic history, the universe was filled with complete stable atoms rather than just naked nuclei and free electrons. But the real miracle wasn't just that atoms formed, the miracle was what happened to light itself. With most of the free electrons now bound up in atoms, photons could suddenly travel freely through space without constantly being scattered. The cosmic fog lifted, and the universe became transparent for the first time since the Big Bang. This moment, occurring roughly 400,000 years after the universe began, represents one of the most profound transitions in cosmic evolution. The light that was released during recombination is still traveling through the universe today. We can detect it as the cosmic microwave background radiation, a faint whisper of heat that permeates all of space. It's like a baby photo of the universe, showing us what the cosmos looked like when atoms first formed. Think about the significance of this moment. Every atom that would eventually become part of a star, a planet, or a living being, was born during this cosmic transition. The hydrogen atom that might one day become part of a water molecule in your cells was created during recombination. The helium atom that could eventually find its way into a balloon at a child's birthday party formed during this same cosmic epoch. But here's where the story gets even more incredible. The atoms that formed during recombination were still incredibly simple. We're talking about hydrogen, helium, and tiny amounts of lithium. These are the simplest possible atoms with just 1, 2, or 3 protons in their nuclei. The universe had successfully learned how to make atomic building blocks, but it hadn't yet figured out how to make the complex atoms that would be necessary for chemistry, for planets, for life. To create heavier elements, the universe would need to build cosmic furnaces far more powerful than anything that existed during the Big Bang. It would need to create stars, massive balls of gas that could generate the extreme temperatures and pressures necessary to fuse light atoms into heavier ones. But stars couldn't form until atoms existed to provide the raw material. This creates one of the most beautiful feedback loops in cosmic evolution. The process began with gravity, that patient architect of cosmic structure. Even though the universe was now filled with atoms rather than plasma, it wasn't perfectly uniform. There were slight variations in density, tiny ripples left over from quantum fluctuations in the very early universe. These ripples became the seeds around which matter would begin to accumulate. Gravity worked slowly but relentlessly. Regions that were even slightly denser than average began to attract nearby atoms, growing more massive over time. As they grew, their gravitational pull became stronger, allowing them to attract atoms from increasingly greater distances. What started as tiny variations in atomic density gradually became larger and larger concentrations of matter. This process took millions of years to unfold. Slowly, patiently, gravity gathered hydrogen and helium atoms into vast clouds that spanned hundreds of light years. These primordial gas clouds were the cosmic construction sites where the first stars would eventually ignite. But even forming these clouds required a delicate balance of conditions. The atoms had to be cool enough to clump together under gravity's influence, but not so cold that they would freeze into solid particles. They needed to maintain just enough thermal motion to remain gaseous, while still allowing gravitational attraction to pull them into increasingly dense concentrations. The universe was walking a tight rope between order and chaos, structure and dispersal. As these gas clouds grew more massive, something remarkable began to happen at their centers. The accumulating atoms were being compressed by the weight of all the material above them. Compression leads to heating, and heating leads to increased pressure. Deep within these cosmic nurseries, conditions were slowly approaching the extreme temperatures and densities that would be necessary for nuclear fusion to restart. But this wasn't the same kind of fusion that had occurred during Big Bang nucleosynthesis. That early fusion had been driven by the ambient temperature of the entire universe. What was happening inside these gas clouds was gravitational compression, the universe learning how to create local hotspots where nuclear reactions could occur even as the overall cosmic temperature continued to drop. The first stars that formed from this process were unlike any stars we see today. They were massive, perhaps a H 100 times more massive than our Sun, and they burned with incredible intensity. These stellar giants lived fast and died young, but during their brief lifetimes they accomplished something extraordinary. They became the universe's first heavy element factories. Inside their cores, temperatures reached hundreds of millions of degrees, hot enough to fuse hydrogen into helium, helium into carbon, carbon into oxygen, and so on up the periodic table. For the first time since the Big Bang, the universe was creating new types of atomic nuclei, building the chemical diversity that would eventually make complex chemistry possible. These first stars were cosmic alchemists, transforming simple atoms into complex ones through nuclear fusion. Carbon atoms formed when 3 helium nuclei collided simultaneously in a process so unlikely it seems almost impossible. Oxygen formed when carbon nuclei captured additional helium nuclei. Neon, magnesium, silicon, sulfur and iron all emerged from the stellar furnaces through carefully orchestrated nuclear reactions. Each step in this process required precise conditions and perfect timing. Most of these early stars ended their lives in spectacular supernova explosions, scattering their newly minted atoms across vast regions of space. These stellar explosions were crucial for atomic evolution because they solved a fundamental distribution problem. Heavy elements created in stellar cores would normally remain trapped inside stars forever, but supernovae are so violent that they can overcome the star's gravitational pull and blast newly formed atoms into interstellar space, where they become available for building the next generation of stars and planets. With each stellar generation, the universe became more chemically diverse. Gas clouds that collapsed to form new stars now contain not just hydrogen and helium, but trace amounts of carbon, oxygen, silicon, and iron. This chemical enrichment meant that subsequent generations of stars could form with solid particles mixed in with the gas, creating the raw materials for planet formation. But the story doesn't end with stellar nucleosynthesis. The universe still needed to learn how to make the very heaviest atoms, elements like gold, platinum, and uranium that require even more extreme conditions than stellar cores can provide. These elements would be forged in some of the most violent events in cosmic history: collisions between neutron stars and other exotic stellar remnants. The formation of atoms from nothing was not a single event, but an ongoing process of cosmic learning and experimentation. Each phase of atomic evolution built upon the previous phase, creating new possibilities that hadn't existed before. Simple atoms enabled star formation. Stars enabled heavy element creation. Heavy elements enabled planet formation. And planets would eventually enable the chemistry necessary for life. What we're witnessing is the universe gradually discovering its own creative potential, learning through billions of years of experimentation how to transform pure energy into the complex atomic structures that make consciousness possible. The atoms in your body are the end result of this cosmic educational process, each one carrying within it the entire history of atomic evolution, from the Big Bang to the present moment. As we venture deeper into this cosmic story, we encounter something that should make your mind reel with wonder. The atoms that eventually found their way into your body didn't just form once and remain unchanged. They've been on an incredible journey, recycling through the universe for billions of years, participating in countless cosmic events before finally becoming part of you. Think about the iron flowing through your bloodstream right now. That iron atom was forged in the core of a massive star that lived and died long before our solar system even existed. It was created under pressures so intense that they compressed atomic nuclei together despite their natural tendency to repel each other. The temperature inside that ancient stellar furnace reached over 3 billion degrees, hot enough to overcome the electromagnetic barriers that normally keep atomic nuclei apart. But creating that iron atom was just the beginning of its cosmic adventure. When the massive star reached the end of its life, it didn't fade away quietly like smaller stars do. Instead, it detonated in one of the most violent explosions the universe can produce. A supernova that briefly outshone an entire galaxy containing hundreds of billions of other stars. During that explosive moment, Your iron atom was hurled into space at speeds of thousands of miles, riding shock waves that stretched across light years of interstellar space. It spent millions of years drifting through